In our current modern world, information is just right around the corner. Large quantities of data are being created every second right now. They say about 1.7 megabytes of data are created every second by every person during the year 2020. That's 2.5 quintillion bytes of data every day that humans produce. As time passes, the data we have to deal with grows exponentially large, making it harder for us to store those. Hard drives, flash drives, and servers are constantly flooded with information. And if it can't keep up, then what do? That's where data compression comes in. Data compression is the art and science of a clever way to represent huge amounts of data into a smaller and more compact form. It's important since it allows accessing and retrieving data quicker as we have to deal with shorter amounts of data. We encounter data compression every day, from making phone calls, viewing pictures, listening to music, and even now as you are watching this video on YouTube. But it doesn't stop there. You might have already done data compression yourself and might have not realized it. Imagine this. You are tasked to make a list of what to buy in a grocery store. However, you only have a limited amount of paper and ink to write it all down. So for example, you are asked to list 4 pieces of bread and 4 eggs on a piece of paper. Instead of writing eggs, eggs, eggs and eggs, and bread, bread, and so on, you can write down eggs times 4 and bread times 4. Instead of taking up 8 lines in the paper, you are only taking up 2 lines, which saves you more than half of the paper for other stuff. Now imagine doing that for 1,000,000 eggs and 1,000,000 bread. You'll definitely save a lot of space with that. There are 2 main types of data compression, lossy compression and lossless compression. The difference between these two is how they are used and what file can they actually compress. Lossy compression can squeeze much larger data, but its main drawback is that it doesn't preserve the full integrity of the file. Meaning, compressed version will somewhat differ from the original, and how much of that is determined by how much you compress the data. Take a look at this photo. If I compress it for about 56%, the changes are not noticeable. But if I bump up the compression, like let's say 80%, you can start to see the image drops in quality. That's because lossy compression works on the concept that we humans can only take in so much information at a time. So, there will be cases where not all frequencies are heard in an audio sample, and not all pixels can be thoroughly seen in an image. Lossy compression gets rid of those small things to achieve a smaller file size. Social media apps like Instagram, Messenger, Facebook, and Twitter are known to compress images. It does load images and videos faster, but at the price of sacrificing quality. That is why some people prefer other services like Google Drive if they need a high-quality version of the photo. Lossless compression, on the other hand, can preserve 100% of the data in a file, but its downside is that it cannot compress as much as lossy compression. Files that are compressed and lossless don't lose quality. Instead, you can recreate the original file from the compressed version. It's as if you're just encoding the bits in a clever manner to represent the data, which is the main concept behind data compression. This type of compression is widely used in text files, JavaScript codes, HTML codes, as well as ebooks and anything that is composed of text. Although it can be used in photos like vectors and GIF, it doesn't perform as well as lossy compression. A good example of lossless compression is Huffman encoding and Rondon encoding. Let's start first with Huffman encoding. Huffman encoding, developed by David Huffman, is an algorithm that involves assigning shorter sequences of codes to variables that occur more frequently in the data. Similarly, variables that occur less frequently are assigned to longer sequences. This technique is actually used in Morse code, so when you encode a message, the most common letters used in the English alphabet are assigned to the least dots and dashes. So, what you're left with is a compressed code and you don't even realize it. To compress data, you'll need to create something called a Huffman tree. A Huffman tree is a binary tree that will generate the corresponding code for each of the characters in our text, and is sort of like an alphabet the computer follows in order to compress the data. To demonstrate, let us try to compress the word data compression. First step is to create a table showing the character's frequency, and then arrange it by descending frequency. The letter A appears in the word data compression exactly 2 times, so it has a frequency of 2, followed by S, and so on. Next, create a node for each of the characters and arrange them by frequency. I'll indicate the frequency by a parenthesis so it won't be confusing. The next thing to do now is connect nodes. When 2 nodes are connected, a new node is created, combining their frequency. So for example, you have a node with a frequency of 2, connecting it to S2 will create a new node. with a frequency of 4. You always start connecting by order of descending frequency in order for this to work. We repeat the same step, except now we combine the nodes with the frequency on it to have a bigger tree. Apply this step repeatedly until all nodes are connected into one giant Huffman tree. Now technically, the Huffman tree is completed. We can verify that it is completed when the top node is equal to the total number of characters in the data we are trying to compress. Now, I'll designate every left path indicated by a 1, and every right path indicated by a 0. To use the tree, we just follow the path from top to bottom until we arrive at a specific character. Every time you traverse a different path, you will end up with a different character and of course a different Huffman code. For example, if you want to find the binary code for the letter S, from the top of the tree, we go 0, then 1, and finally 0 again. We now assign the binary code 010 to S, so every time the computer encounters 010 in the code, it will translate to S. We do this for all of the letters in the word and arrange them in a table. Encoding the word data compression using the table will result in a code which only takes up 53 bytes of data, compared to the standard ASCII code which takes up about 120 bytes of data. This is of course ignoring the storage for the Huffman tree. But in large quantities of data, the Huffman tree only takes up a small percentage of the total size. Now, if you want to compress images, you might be interested in run length encoding. Run length encoding, or also known as RLE, is a lossless compression which takes advantage of the running length of characters in the data. Running length is defined as how many times a character is repeated in a row. For example, if you want to compress this text, you can represent it as E12G6. The same thing is applied to pixels in a picture. Let's bring out a 15 by 10 image. Suppose that every pixel is about 5 bytes, then this whole image is 750 bytes. The numbers you see in the pixels are the color represented in numbers. Now, watch what happens if we try to compress it using RLE. We take the color of the pixel and combine it with its running length. The format is the pixels followed by the running length, and we have to be consistent so the computer knows what corresponds to what. We do this for each of the row, and it's going to look something like this. Now, we assume that each number is 5 bytes. If we count how many numbers per row we have, the image can be represented in as little as 460 bytes. Although, there are some drawbacks to this. Look what happens if we shuffle the pixels randomly and try to compress it again. The result would be 1380 bytes. The compressed file is actually larger than the uncompressed version, which is very bad. You just added useless data which wastes time and money. That's why it's really important to apply the right compression algorithm to different file types or even combine them to maximize efficiency. There are dozens of algorithms that you can find that are much more complex than what we discussed, like PNG and GIF formats. To summarize, data compression is the science of squeezing larger data into smaller sizes. There are two types of data compression, which are mainly lossy and lossless. Lossy is used in photos, videos, and audio samples, while lossless is used in data, mainly composed of text, codes, and anything that cannot have errors in them. Data compression is one of those things that is often taken for granted, especially today that every field is now gearing towards incorporating advanced technology in their research. Data compression becomes more relevant and significant in this era. As time goes by, more and more people shift toward online learning, which utilizes online resources which make use of data compression. Databases, servers, online trading, online banking, and even online classes are slowly becoming the new normal in our lives. Without data compression, I can't even begin to imagine how things will be. Thank you for watching. I hope you learned something from this video. Now, the next time you watch a movie online or view an image on your computer, think data compression for those faster load times and smaller file sizes.